Hi, welcome to the second part of the solution to this exercise that we have been discussing already. This is an L-shaped beam, and we were asked to calculate four things basically, or position direction of the principal inertia axis, a magnitude of the principal moments of inertia after we have found those, how those principal inertia axes are oriented. And then we're asked to find the direction of the neutral axis and maximum stresses presented after we have found that neutral axis. Now, there is something important here is that in the last video, I ended up just by defining the orientation of the principal inertia axis. And let me just correct this. This is not going to be right. Well, it is right, but just let me write it better. This is the axis U prime or UU, and this is V here. So instead of writing IU and then IV, so we have these ones here. So, but I mentioned that we covered these two points, but it's not true. So we are missing still to calculate the magnitude of these principal moments of inertia. And to do that, we need to rely on the similitude that the principal, or the definition of the principal axis with the principal stresses, something that we took a look in the lectures. And just by bringing that formula where we were using Mohr circle to calculate that, we're not going to use Mohr circle, we're just going to use the formula here. So the moment of inertia around the first principal axis, inertia axis, is going to be, again, is a similitude with the principal stresses formula, and it's going to be equal to this one here, plus axis about y, this is divided by 2. Then we're going to have the subtraction of these two terms minus this one here, divided by 2. That's going to be multiplied by the second of the double angle there. So we have the angle, so we already know the double angle. And yeah, let's apply the formula. So it's going to be, let me write it down here better. U equals to, let's put the values. So everything is millimeter to the power of 4. So I'm not going to write the units in this case, just the values. 12500 plus 412500. Again, this is divided by 2 plus the subtraction of these two terms, 412500, minus the moment of inertia around the, sorry, this is not correct. Why am I writing like that? Because 1512500 minus now moment of inertia around the y-axis. Divided by 2 times the second of the double angle, but the double angle is already here, so second of 140.72 degrees. Great, let's calculate that. Let's go to GeoGebra to calculate it. Let me fix this a little bit better. Yeah, let's go to GeoGebra. Okay, let's see. Well, I deleted the previous values, so let me write it down again. 1512500. We have I y, and that's equal to 412500. Then I'm going to have theta. Can I write? Yeah, but if I can, 100 or 2 theta. 2 theta equal to 140. No, let's do it correctly. Theta equals 70.36. And then we can do it as I u is equal to fraction I xx plus I y divided by 12 plus fraction again I xx minus I moment of inertia around the y-axis divided 2. Now this is not 12. Why did I write 12? And then this multiplies here times the second, there it is, of 2 times theta. Now this is the value we're getting, so there may be a little bit of differences with respect to the exercises you have my solved during the practice sessions, but it's because of the decimals. They influence a lot here, so don't worry about that. Let's go back to OneNote to write down this value. And then this is going to be equal to 27,739. And this is going to be in millimeters to the power of 4. Yeah. Perfect. So now how do we find the other moment of inertia around the v axis? And let's remember that we have this equation that allows that it's a balance, some sort of balance equation that says that, well, you know what, the sum of the moment of inertias, be correct, kind of those calculated around the principal inertia axis have to be equal to the sum of any other moment of inertia, taking into account any other axis here. So from this equation, we can say that this value here, yeah, equals to xx plus moment of inertia around the y-axis minus the one that we have just found. Keep writing the w. Okay. So this is equal to what? Well, let's write them down. So it's 1512500 plus 412500 minus 270739. And all of that is going to be in millimeters to the power of 4. Let's go to GeoGebra to make this calculation here. Where am I in here? Yeah. So then VV this equals to this moment of inertia plus this moment of inertia. So it should be XX minus the recently found moment of inertia. There you go. This is the value that you should more or less get. And let me write it down. So I'm going to back to OneNote. We have that this equals to 1654260.9. Going to single them out because we are going to need them. This one and this one here. Perfect. So now, yes, now we have a given answer to the second point. So the magnitude of the principal moment of inertia about these axes here, u, v, v, are these found here, those ones. Perfect. Now, what's next? Well, now they're asking us, well, consider that this profile is used in a cantilever arrangement of 1 meter length, and there are 2,000 newtons applied at the free end. So calculate now the neutral axis and the position of, and then the maximum stresses that are found there. Yeah. So let's do that. Should I bring this figure? Let me bring this figure because we're going to need it. And then I'm going to draw another figure that's going to help us. Let me see if I can bring it here. Yeah. Let me clean it out a little bit because there are many things that we don't need here. For example, we don't need these ones that we were defining. Need that one. This one. No, it's too close. Okay. This one. Just clean it a little bit. So, no, not this one. Neither this, I think. And this either. Or this. If I need them, I will draw them again. Yeah. Let me get rid of this. A little bit better. We change the erasers so we can get rid of this one, this one. Yeah, perfect. So to calculate, so let's draw first the cantilever arrangement, and it's going to be something like this. I'm going to have here, the free end in here. Well, sorry, the fixed end, and then I'm going to have these 2,000 newtons applied at the free end, and the distance between or span of this is 1 meter or 1,000 millimeters. So that is it. Perfect. So we already we need to play between calculating stresses and calculating the final position of the orientation of the neutral axis. Because if we remember the formula to calculate the position of the neutral axis, we need to bring the definition of stresses here. And for example, when we talk about the normal stresses caused in this unsymmetrical bending case, it's going to be equal to what? Well, it's going to be equal to the moment around the v-axis times u. This is all extracted from the lectures. They're divided by the moment of inertia around the v-axis plus the moment around the u-axis times v divided by the moment of inertia around the u-axis, principal inertia axis. Now, one of the things is that to know the stresses, you need to know the points u and v of the point of interest that you want to calculate the stresses on. But as we are dealing with the orientation of the neutral axis, one definition that comes of neutral axis is that axis or surface where stresses are zero, meaning that I would need to use this equation here and say, well, whenever this happens, this one here, then I'm going to find where the neutral axis is. Yeah, perfect. So if I wanted to do this, I would need first to calculate the moments and basically the moments. So to calculate the moments, we can do it in two ways. What I will do it one simple way is that I'm going to take the 2000 newtons load applied at the free end, and I'm going to decompose it from the y-axis into onto the u and v axis. Yeah. So let me bring this triangle better. I'm going to use the same colors. So we have this triangle here, first one, and then I've got maybe this one here, and I got this one here. So this is the v axis, this is the u axis, and this is the y axis. Okay. And the force, well, the force is applied here. So let's put it like this. The force, let's call it F. And I know also that this angle here is theta, the one that I have just calculated. All right. So the projection of F, pick a color here, onto the UU axis is equals to what? Well, it's equals to F sine of theta. The projection of F onto the VV axis is this one here. Great. And we said that this is passing through the centroid of the section. So this is a very nice application here. Now, the moment around, let's say, U axis is the one caused basically by the force VV. Yeah. So for example, this force here is going to make the piece turn around the UU axis. It means that the moment, the color, the moment, just pick this one, around U axis equals to what? To the force VV times the length of the application of the beam, because we're talking about this resistance tensor here. So something like this moment here. But as the length is 1, so we can just keep it like that, or no, let's put no, the length is 1000. And then the moment around the V axis is going to be that force U times the length. Let's give some values here. U equals to the force, which is 2000 newtons, times sine of the angle. And the angle we said was, where is it? 70.36. Sorry about this. We're talking about this FBP. Cosine of the angle, 70. Again, sorry about that. Okay. Times how much? 1000 meters. Sorry, 1000 millimeters. Then this moment is going to be equal to something. And let's go to GeoGebra to calculate it. Let's continue here. So MUU is going to be equal to 2000 times 1000 times cosine of 70. Actually, I have it as theta. There it is. So this one is, I'm going to go back to one node, and that's going to be equal to 64.0199. Yeah, let's keep it like that. 0.3. Let's round it up to 1.4. And this is in what? Is in newtons per, or newtons millimeter. Now for the case of MVV, I have similar 2000 newtons sine of the angle we're dealing there times 1000 millimeters. Then this value of this moment is going to be, let's go back to GeoGebra, let's call it MV equals to 2000 times sine of theta. Let's write it down, same as the other one, 1000 times. Yeah, let's go back to one node. And this is going to be equal to 18,94767.7. Yeah, beautiful. Then let's construct this equation now. And we're going to have that in here, sigma, which is, well, this is the general equation for stress. And this is going to be equal to what? Well, I wrote down differently the moments, but the idea is that, and let me make it equal so we don't get confused. We're going to have that 18,94767.7 divided by the moment of inertia, and that is, let me see if I can copy it from GeoGebra without disrupting this one here. Yeah, in here. So it's 1,654,260.9. Yeah, and this multiplies U plus MU, which is 640199.4, divided by the other moment of inertia, which is 270739. I believe I left it at that point, yeah. And this multiplies V. The units of these whole equations are presented, if we have at the top newtons millimeters, and at the bottom we have millimeters to the power of 4, then this is going to be newtons divided by millimeters to the power of 3. This is the unit of this equation here. But as the U are going to be presented in millimeters, then I can already move this to the 2. And then we're going to have an equation in equivalent values of stress there. But perfect. But what is the orientation of the neutral axis? Well, that's easy, because if we make this equal to 0, as we said for the neutral axis, we're neutral, then I'm going to end up with a nice relationship. So let's go to GeoGebra and calculate these fractions here and see how it turns out. GeoGebra, so the first fraction is going to be M, I called it VV divided by IV, yes. So this first part is 1.415. Again, here I'm going to have 1.45 U plus the other fraction. Let's go back to GeoGebra, and that's going to be MU divided by IU, and that's going to be 2.36. Let's go back to one node, and this is going to be equal to 2.364 V, and that's equal to 0. Great. Now, if I consider that, if I want to know what's the orientation, this, as it is looking, if we imagine, for example, in our typical problems, that this is equivalent to the x's and this is equal to the y's, then I could form some sort of relation, get to know y in terms of x or v in terms of u. And the reason for that is that when I isolate this v, this is going to end up being what? Minus 1.145 divided by this 2.364. phi, and sorry, u. And this is an equation representative of a straight line. Yeah, the one that we have like x equals to m times x that crosses the origin, that passes through the origin, be the origin our point G here. So it means that this m represents the tangent of the angle of the slope, meaning that if I say, well, m equals to what? Well, is the relation between these two values. So let's go back to GeoGebra. Where am I here? So it's going to be minus 1. Sorry about that. Minus 1.145 divided by 2.364. Okay, so that is minus 0.48. Let's go back. And let's call that m. Yeah. So we're here back, so that is minus 0.484. Now I know that m is equal to the tangent of the angle of the slope of that, or the inclination of the straight line, meaning that I can know that the angle then is going to be the inverse of the tangent of that minus 0.484. And that's going to be equal to what? Let's go back to GeoGebra. So it's the our tangent, let's see, there it is, of m. So this is alpha, minus 25.84. Let's go back. Then this is alpha equal to minus 25.84 degrees. And what this is saying, kind of similarly with the other case, that the neutral axis is oriented at minus 25.84 from the u-axis. That is, let me write it down. So let me make a quick calculation here. 7.36 minus 25.84. I'm just doing it offline, so it's 44. So it means if I bring the ruler in here, we go back to here. So it's going to be about 44, 45, something like this. This is going to be the orientation of the neutral axis. There. Going back here, 25, how much was it? 25.84, negative, yeah. 25.84 degrees. Excellent. Now we have given answer to point number 3 here. And the next to do is to find out what are the maximum stresses appearing here. And then when we look at the points or the construction of the L shape from the point of view of the neutral axis, well, we know that the farthest away points are going to be actually this one, 0, this one. And let's change the name and let's call it L. And we're going to have the farthest away point from the neutral axis on the top is going to be this one, so M, uppercase M. This, as it is applied, this cantilever, in this cantilever application, how the force is applied, it means that this M is going to be in compression. And this L is going to be in tension. So what is left to do is to find these distances here. This one here, measure with respect to the U and V axis here. This one here, and this one here. And the same for the M point here. So more or less something like this. We move it like this, and then this one here. Those two distances. I'm not going to mark it yet, but those are the two distances needed. Now, I will draw a triangle here to explain how to go from the XY coordinate system to the UV coordinate system. And for example, let's say that this is the more or less like this. this representing the U axis, and then we have this line here representing the x-axis, and this one representing the y-axis. So this is y, and this is x. Now, I could draw a perpendicular to this line, to put it like this better, and from here to here. And as I want to know what's the value of u, because in my equation, of stress equation is represented kind of a value in u and a value in v. So if I want to know what's the value in u for any specific point, then that means that to go from here to this value, let's call it u again, even though this is the same axis. So I know that I would have to walk a certain path here. So this is theta, as we know, and this is the other angle corresponding kind of the complement of the angle when we take into account this internal sum of this straight triangle. Then we're going to have this that u here equals to what? Well, it would be kind of having taking this as a hypotenuse here. So it would be kind of x times the cosine of the angle theta. So that would cover, or that would take me from here to here. And then this other piece, it would be covered by this other relation, which is y sine of theta. And that would cover this small piece, that kind of segment in here. Now, if we do the same for the point or the orientation at V, I could do it maybe here, yeah, or a point in the V axis. So let me try to put it more or less perpendicular to this other one, like this. Then I will have the representation of the x-axis, which in this case, let's remember that this is the G, or the centroid of the combined cross-section, which means that these values are going to be negative, and I'm going to have this one representing the vertical axis y, this is x, or minus x in this case. And so what we're going to have here is that this is now the angle theta. Now, if I want to form what's a point from, or how to go from the origin G to a point V again, let's call it, because it's represented on the V axis. So that's going to be V equal to what? To, well, let's put the positive first. That's going to be y cosine of theta minus x sine of theta. So this relation, these two equations are going to help me move from the xy coordinate system to a specific position in u and v. So let's see. Do I know then the x and y positions of points L and M with respect to G? Well, maybe not directly, but I can know it right away, because I know that G, for example, is 15 millimeters from this vertical segment here, this wall here. So this in X, if I want to go from, for example, from this, how to call it, this centroid to kind of to L, so I would have to go minus 15 millimeters, and then I would have to go up this value here, y var, which is 35 millimeters, if I remember correctly. Just let me check that. So we have 35, yeah. So meaning that the coordinates of point L, I'm going to write it down here, are minus 15 millimeters plus 35 millimeters. And now these coordinates are, if I input these coordinates in these two equations, that would give me the coordinates E and V, and then I could put that into the stress equation and get the values for it. Then let's find out now the coordinates of point M. So in point M, I have to, from G, I have to move, how much is that? Well, this little bit here, I don't know if you can see it, this small piece that I'm just kind of moving with the pointer of the pen. So if I know that the wall is 10, and the distance from the thickness of this piece is 10, and the distance from the wall to the centroid is 15, then it means that this is going to be 5. So I have to walk minus 5 in that direction to get the values of it. So let me write it down here. Minus 5. And then the vertical coordinate is going to be, I need to go down all the way to the bottom here. And I already have calculated it before for other reasons, but in this case, I have to travel down in the negative direction 75 millimeters. So this is going to be here minus 75 millimeters. Now, let's calculate the coordinates u and v of these points. So for example, a point L. In point L, if I'm going to study point L, so I'm going to know that u equals to what? Well, it's going to be minus 15 cosine of theta, which is 70.36, plus 35 times the sine of theta, which is this again, 36. Then U is going to be equal, let's go to GeoGebra here. I'm going to call it UL, and that's equal to minus 15 times cosine of, I have theta, I guess, yeah, plus 35 times the sine of theta. And we get that that's 28. I'm going to go back to OneNote to write it down. And just let's put it, we're talking millimeters, so let's just keep it simple, 28.4 millimeters. Now, V is going to be, for the point L, it's going to be, what is minus 5. Sorry, this should be, we're talking about the Y, and the Y is 35 times cosine of the angle here, theta, minus X, that is minus 15, times the sine of the angle theta. So V equals to, let's go back to GeoGebra in here, so call it VL. So it's 35 times the cosine of theta minus, let me write it back again, just messed it up. So 35 times the cosine of theta, or minus 15 times the sine of theta. And we get 25.4. Let's go back to OneNote. So this is 25.4 millimeters. So let's check this, because so the point L is going to be in UV coordinates 28.4, 25.4. So let's go back here. So it means that if I want to go from G to the point L, I would have to travel 28 something in U, and then 25 something on V. So it means that, well, this makes sense. So because now these are two positive, this is the first quadrant, so both coordinates should be positive. Now let's do the same for point M. Point M. Then we have here U is going to be equal to what? 2x, that is minus 5, cosine of theta, plus y, that is minus 65, sine of theta. Then U is going to be equal to, let's go back to GeoGebra, and to write U M, well, small m, equal to minus 5 times the cosine, okay, take this out of the way, of theta, plus minus 65 times the sine of the theta. And it's giving me minus 63.2, let's call it. So minus 63.2 millimeters. Let's go to point V. So V is going to be equal to what? Well, it's Y minus 65 times the cosine of theta. Very right, isn't it? Yeah, cosine of theta. I'm using the correct one. Yeah. Minus X, but X is minus 5 times the sine of theta. 70.36. Then V is going to be equal to, let's go back to GeoGebra. VM equals to minus 65 times the cosine of theta minus 5 times the sine of theta. and that gives me minus 16.1, let's call it. Minus 16.1 millimeters. So again, I'm going to write it down here. So coordinates in U and V are minus 63.2, comma, minus 16.1. So let's make a visual inspection here. So minus and minus, third quadrant. So, well, the point is in the third quadrant, so it means that both coordinates should be positive, negative. So we have it here. Okay, perfect. Now, having those 2 points, we are ready to go to the stress equation and find out how much are those stresses. So let's go in here. So stress in L. Stress in L is going to be 1.145, coordinate in U, and that coordinate in U is 28.4. Yeah, and plus 2.364 times coordinate in V, and that's 25.4. Then sigma L is going to be equal to, let's go to GeoGebra. Sigma L is 1. I should have kind of built this equation, well, form this equation here, but I don't have it. No. I have B and C. Okay, I have B and C. So it means that I could use B times U L plus C times U V. Yes, so that's giving me 30, how much? Is it correct? I think so. Am I using the correct ones? Let me see. B and C. Yeah, I'm using then UL, VL. How did I call it? My bad. UL, VL. That's the value, yeah. So we're having 92.57 newtons per square millimeters there. So let's go back to one node. 92.6, let's call it 92.6 newtons per square millimeter. Now, sigma m is going to be the same kind of approach. We're going to use the stress formula. We're going to have 145. Then this is going to be minus 63.2 plus 2.364 times minus 16.1. Then sigma m is going to be equal to, let's go back to GeoGebra. Sigma m equals to then B times UM plus Z times VM. And there we're having kind of, this is the other stress that we were looking for, and that is 110.4, let's call it negative, because it is in compression as we assumed. So here, this is going to be minus 110.4 newtons per square millimeters. And there we have found our remaining 2 values to complete the exercise. Then as a brief summary for this part, after we found the position of the neutral axis as information, visually you can inspect, in this case it's easy, what are those points that are far away from the neutral axis? And we know that L and M are those 2 points far away from the neutral axis. And according to the loading case, as we have presented here, and let me draw the internal section, for example, if seen from here. So the internal section is going to be something like this, and like this. So this is going to be the kind of how the section is represented if I look it from this point of view here. So it means that this force is going to create, now that we have the neutral axis, we know that this force is going to create a tension on the point L, kind of the farthest away point above the neutral axis, and then it's going to create a compression at point M, the farthest away, below the neutral axis. Then we need to inspect those 2 points. Then having that, and having also the stress equation, the transformation that we need to do at this moment is how to represent my x, y points into u and v coordinates. And for that purposes, what I did was kind of extract a triangle with the u, x, and y, and v, x, and y, and try to see how could I form a distance, for example, in u by using x and y coordinates, and then how to form a distance in v on v by using x and y coordinates. So this is represented in here. After that, what we did was to locate x and y coordinates of L and M points by using G, or the centroid of the combined cross-section, to form those coordinates. And they are represented in here. Now, after that, what we need to do is to transform that from x, y into u and v as proposed here. And then for L, we found those two coordinates. Both are positive, meaning that they are in the first quadrant, which makes sense and is correct. And then for point M, this gives us these two coordinates, which are negative, because they are in the third quadrant, which is also okay visually, is happening, because remember that I tried to draw these, or the orientation of these lines at as much a scale as possible. So these should be around 70 degrees. So these values are pretty much scale. So that allowed us to have certain certainty in locating visually these points. Then after having these points, I took the stress equation and substitute both points into it, and it gave me that, well, we're going to have at L 92 newtons per square millimeters, and this is in tension. And then at point M, as we suspected, it's going to be minus 110 newtons per square millimeter, and this is going to be, finalize this, in compression because of the sign here. Perfect. And now this completes all the 4 questions presented in this example. I can mark it here. It's a pretty interesting example. I believe it's very practical, because it might be possible that you find yourself in situations where you need to do this because values are not given, and you would need to do some kind of calculation work in order to find or certify what are these stresses, if they are within the range, and so on. And remember that this is possible to be done like this, because this is for this specific case. Now, if we're talking about, for example, a simply supported beam, or we're talking about a different loading case where the load applied is different or oriented differently, then you have to take that into consideration to build all this procedure. But the procedure is the same. And I believe that's going to be the end of this session. And I hope that this helps you to kind of take it as a methodology to solve this type of problems, and then to solve those problems given as evaluated exercises. Thank you.